Hey guys, before we can evaluate for trigonometric limits, we're going to need to know how to simplify and rewrite trigonometric expressions. So let's start with a couple of examples and then we'll go into greater depth for some other techniques. For this first one, we have cosine theta cotangent theta minus cosecant theta. The first thing you should try is to take all of your trigonometric functions and rewrite them using only sine and cosine. So here we have cosine theta, so I'm just going to keep that because it's already cosine. Cotangent is when you have cosine theta divided by sine theta minus cosecant theta, which is the reciprocal of sine, so 1 over sine theta. Now, this is basically like we're multiplying fractions, this first part. So we have cosine times cosine, which is cosine squared theta. Cosine squared theta, by the way, is just another way of saying cosine theta squared. These mean the exact same thing. Over sine theta minus 1 over sine theta. Now, since both are over the same denominator, we can write this as one fraction. The numerator being cosine squared theta minus 1, because of the minus 1 here like that, and everything is over sine theta. Now, whenever you have a trig function that is being squared, that means we may need to use a Pythagorean identity. The Pythagorean identity that uses cosine squared is sine squared theta plus cosine squared theta is equal to 1. Now, if you look here, cosine squared theta minus 1, if I use my Pythagorean identity and I subtract cosine squared theta, I get that sine squared theta is equal to 1 minus cosine squared theta. So sine squared is equal to this. So that means I can take this, which is this part here, and replace it with sine squared. So let's try that. So this would be, instead of cosine squared minus 1, I'm replacing it with sine squared theta, which is over sine theta. As a reminder, sine squared, that's like saying sine of theta squared, which is also the same thing as saying sine of theta times sine of theta, which is all over sine theta. So I can cancel one of these signs. And the only thing that's left is sine theta in the numerator over 1, which is just sine theta. So I took this expression, and now it is just equal to sine of theta. So that's what I mean by simplifying. We're making it smaller in some way. Let's try this other one here. Cosecant theta minus cotangent theta. Cosecant is 1 over sine theta times secant, which is 1 over cosine theta, minus cotangent, which is cosine theta over sine theta. So now let's see what we can do with this. These are being multiplied. So we multiply numerator with numerator, which is 1, and then sine times cosine, which is sine theta cosine theta, minus cosine theta over sine theta. Now, in order for me to be able to subtract this, these are both fractions, they need to have a common denominator. They both have sine, but this one has cosine. So that means that I'm going to have to take this fraction here and multiply the denominator by cosine as well as the numerator by cosine. So let's rewrite this now. This is 1 over sine theta cosine theta minus cosine times cosine is cosine squared theta over sine theta cosine theta. Now this is all the same. Since these have the same denominators, I can write this as one fraction, where the numerator would be 1 minus cosine squared, and the denominator would be sine theta cosine theta. Now look here, 1 minus cosine squared popped up again, which we know is equal to sine squared. So I can substitute that numerator with sine squared theta over sine theta cosine theta. Remember that sine squared means there's two sines, so I can cancel one of them and that will get rid of the exponent because now I've taken one away. So this is now sine theta over cosine theta, and sine divided by cosine is equal to tangent theta. So this would be the simplified version of this expression. Let's try another technique. So all I've done here is I've rewritten each of these trig functions using only sine and cosine, and then seeing what happens. For this next technique, we're going to simplify by factoring. These are these Pythagorean identities that we were working with in the previous slide. The most commonly used one is this top one. Sine squared plus cosine squared is equal to 1. Now let's see. Here we have sine squared theta cosine theta minus cosine theta. I notice that both of these terms have a cosine theta in common. So what I can do is I can factor out a cosine. So this will be cosine theta times sine squared theta minus 1 is equal, oh that's it, sorry. Now sine squared theta minus 1. If I look at this Pythagorean identity, we have sine squared plus cosine squared is equal to 1. Now, whenever I need to use a Pythagorean identity, I see this expression, sine squared theta minus 1, and I see that I could probably get that from this identity by rearranging some things. So what I can do is I can subtract the 1 and move it to this side. So this is sine squared theta minus 1 plus cosine squared theta is equal to 0. And then if I subtract the cosine squared theta, I get this. Sine squared theta minus 1 is equal to negative cosine squared theta. So here is that sine squared theta minus 1, which is equal to negative cosine squared. So I'm going to replace this with this. So now let's rewrite it. We have cosine theta times negative cosine squared, squared theta. If you multiply cosine with cosine squared, that means that it would be negative cosine cubed theta. Since remember, you're adding exponents when you multiply. So this would be my simplified answer. Let's look at this last one here. We have negative secant theta minus tangent squared theta secant theta. Both of these terms have a secant in common. Additionally, they're both negative. So I am going to factor out a negative secant theta, which will leave me with 1 plus, because I took out the negative, tangent squared theta. Now I don't need to rewrite anything, because if you look at the Pythagorean identity, 1 plus tangent squared is the same thing as tangent squared plus 1, which is equal to secant squared. So I can replace the 1 plus tangent squared with secant squared. So this will give me negative secant theta times secant squared theta. And when we multiply negative secant with secant squared, that would give me negative secant cubed theta. Now let's just practice a couple more examples. Here we have cosine x plus tangent x sine x. So we're going to first try to rewrite everything using only sine and cosine. This is already cosine x plus tangent, which is sine x over cosine x times sine x, which I'm going to put it over 1 so that we can multiply this out. So this gives me cosine x plus sine times sine is sine squared over cosine x. Now in order for me to add these two together, this is over 1, we need a common denominator. My common denominator here would be 1 times cosine, which is cosine x. So I need to multiply this fraction here, the denominator, by cosine x, as well as the numerator by cosine x. So what that would give me, cosine times cosine is cosine squared x over cosine x plus sine squared x over cosine x. Now that they both have the same denominator, I can write this as one fraction. This would be cosine squared x plus sine squared x, and everything is over cosine x. Now these are squared. This is a Pythagorean identity. If I go back, cosine squared plus sine squared is the same thing as sine squared plus cosine squared, which is equal to 1. So I can replace the numerator, this, here with 1. And that would give me 1 over cosine x. And if you have cosine x in the denominator, this means that this is equal to the reciprocal of cosine, which is secant x. Let's look at this last one here. We have 1 minus sine squared theta over 1 minus cosine squared theta. Now these are part of Pythagorean identities. 1 minus sine squared we've seen before. I'm going to come back here a second. Well, we haven't seen that one before. Let's just use our Pythagorean identities. This is my identity. Sine squared theta plus cosine squared theta is equal to 1. I want to see what I can replace this with. If I subtract sine squared theta to both sides, I get that 1 minus sine squared is equal to cosine squared. Now the same thing goes with 1 minus cosine squared. This is my Pythagorean identity. If I subtract cosine squared to both sides, I get that 1 minus cosine squared is equal to sine squared. So I'm going to replace what I got here to rewrite this. 1 minus sine squared is cosine squared over 1 minus cosine squared, which is sine squared. And this is being multiplied with tangent. And tangent is sine divided by cosine. So now what happens here? This means that there are 2 cosines. This means that there are 2 sines. I can cancel out one of these sines, and I can cancel out one of these cosines. So I'm left with 1 cosine left in the numerator and 1 sine left in the denominator. And cosine divided by sine is cotangent theta. Let's look at these last 2 examples. Here we have sine squared minus cosine squared times sine squared. Both of these terms have a sine squared in common, so we can factor out a sine squared. When I do that, I am left with 1 minus cosine squared theta. Now this 1 minus cosine squared we've seen before for sure. 1 minus cosine squared is equal to sine squared. So I can replace that 1 minus cosine squared with sine squared, which is being multiplied with another sine squared. So sine squared times sine squared, we add those exponents and we get sine to the fourth of theta. Now this last one is a little special. We have 1 over 1 plus cosine x plus 1 over 1 minus cosine x. If we ever have a fraction plus or minus another fraction, we need the LCD, the least common denominator. Which, remember, if you can't figure it out, you just multiply those denominators together. But I'm not literally going to multiply it out right now. 1 plus cosine x and 1 minus cosine x would be my LCD. So now I want to rewrite so that both of these have the same denominator. So this is my original equation. To the first fraction, I am missing a 1 minus cosine x. So I'm going to multiply both the numerator and the denominator by that missing factor. For the next fraction, 1 over 1 minus cosine x, I am missing the 1 plus cosine x from the least common denominator. So I'm going to multiply that to both the numerator and the denominator. Now let's write this as one fraction. Or rather, let's just write this again with our new denominators. So this numerator is now 1 minus cosine x over 1 plus cosine x times 1 minus cosine x plus 1 plus cosine x, and the denominator is now the same as the other one, so 1 plus cosine x, 1 minus cosine x. Since they have the same denominator, we can combine this as one giant fraction and add the numerators. So 1 minus cosine x plus 1 plus cosine x all over 1 plus cosine x, 1 minus cosine x. If you look at the numerators, the cosines will cancel. And I'm left with 1 plus 1, which is 2, over, now let's multiply these out. You should recognize this as a difference of squares that was factored. But if you don't, that's okay. We can multiply it together. This is 1 times 1 minus cosine x plus cosine x minus cosine squared x. Negative cosine x cancels out with positive cosine x, and I'm left with 2 over 1 minus cosine squared x. Now 1 minus cosine squared, we see here, is sine squared. So I can rewrite this as 2 over sine squared x, which if you have sine in the denominator, we can bring that up because the reciprocal is cosecant. And since sine is squared, this would be cosecant squared x. And that's our final answer. And that's simplifying and rewriting trigonometric expressions.